This is Stat 101, Examples Class 10. Example 3, using a paired sample t-test to determine mean difference. And we'll use Excel to do this problem. This problem relates to blood pressure. Many people have a high anxiety about visiting the dentist. Researchers want to know if this affects blood pressure in a way that the mean blood pressure while waiting to see the dentist is higher than the mean blood pressure an hour after the visit. So 10 people have their systolic blood pressure measured while in the dentist waiting room, and again an hour after the visit. So we're looking to test this research hypothesis, making an assumption that the differences are approximately normal. Now, why are we using a paired test in this case? What we're looking at here is 10 individual people who have their blood pressure measured before going to the dentist and then again afterwards. So we have individual variation here amongst all of those observations. So we're testing the research hypothesis that the mean blood pressure whilst waiting in the dentist waiting room is higher than an hour after the visit. Now we're going to go into Excel, where we have already posted these values inside of Excel. So we have 10 individuals and we have their blood pressure before and after. In order to make differences, and what we're looking at here is the difference between the blood pressures, I've used blood pressure before minus blood pressure after for those differences. So inside of Excel we can use the blood pressure before using cell references minus the blood pressure after, and that will give us a difference of 14 for the first person. Now, copying those cell values right down to the bottom, the individuals will be found by moving on blood pressure before minus blood pressure after for each of the observations. And of course we can do the sum of those differences by using the sum formula in Excel and the sum of the differences from first person down to the 10th person using the sum formula. It gives us 57 as the sum of the D's. Now, of course, the other thing that we need for the calculations here is the squares of the differences. So we can square those differences, again, by using a formula in Excel, using cell reference for the first person, D3, and squaring that value. So again, copying that cell down for all of the individuals gives us the squares of each of those differences. So any time that the calculations are complicated, there's no reason why you can't use Excel. Again, we're going to sum these, so we've got the sum of the squares of the differences, and you'll see why we need those when we come to look at the formula. So we've got the sum of the D's, the sum of the differences, 57, and the sum of the D squares, 651. Now, coming back to our example, if we come to look at the calculations for that paired sample t-test, we need to be able to find the paired sample mean, the X bar for the D's, and we were using here from Excel, we got the sum of those differences as 57, and the sum of the D squares was 651. Now, using the formulas for the mean difference here, we're looking at the mean of the differences, which is 1 over n. I know we had 10 people in our sample, 10 observations, so n equals 10. 1 over 10 multiplied by the sum of the differences, which was 57. 1 over 10 times 57 is 5.7. So the mean difference for the observations is 5.7. Now, to find the standard error, we begin by finding the standard deviation squared for those differences, and the formula there, using the standard deviation squared or variance formula, 1 over n minus 1. Now remember, n is 10, so we have 1 over 9, multiplied by the sum of the D squares, 651, minus n, which was 10, multiplied by the square of the mean difference, 5.7 squared. Now the calculation for 5.7 squared multiplied by 10 subtracted from 651 gives us 326.1 on the top line, divided by 9, giving us 36.233 for the variance of the differences. Now, in order to find the standard deviation of the differences, SD, we will square root that variance. Square root of 36.233333 gives us 6.0194. That's the standard deviation of the differences. And to find the standard error measure for this formula, standard deviation divided by the square root of the sample size, SD divided by the square root of the number of differences for the standard error measure, that's 6.0194 divided by the square root of 10. And that calculation comes out at 1.9035. That standard error measure goes into the formula for the test statistic. Again, the test statistic here for the mean difference for paired populations is x bar for the differences, which was 5.7, minus the hypothesized mean difference, which in this case is 0. Our hypothesized mean difference was 0. We're assuming no differences, so hypothesized mean difference of 0, divided by that standard error measure, which again that we had down at the bottom of the right-hand side of the screen, 1.9035. And that calculation for the test statistic comes out to be 2.994475, very close to 3, a large number of extra values given there. So also one more thing here to get the degrees of freedom for our test statistic, and when we're coming to the critical value here, number of differences minus 1, so that's 10 minus 1, which is 9 degrees of freedom. So now we're going to take our degrees of freedom and the test statistic over onto the next slide. No, we're not, are we? We're going to go to Excel first. So in Excel, in order to do this problem, we can use the data analysis, which, if you don't find it, has to be found from the Excel options. And of course, when we go to add-ins, we can get that data analysis from the tool pack. So Excel add-ins, okay. And to be able to use Excel to do this paired sample t-test, what we're doing is we're working through the data analysis until we get to the t-test. So you'll notice there are 3 t-tests. The first of those is the paired 2 samples for means. So we'll choose that and click OK, and it brings us to the dialog box. So we're using the input variable 1 range, which we would be using the BP before, that's the before. Blood pressures, so using that column B, blood pressure before is variable 1 range. Blood pressure after is variable 2 range, so choosing column C, the observation values. Hypothesized mean difference has to go in now, and of course we're hypothesizing a mean difference of 0 or no difference, so we put 0 in there. Now we didn't have any alpha value specified in this example, so we'll use an alpha value of 0.05. It's the default in Excel, and we'll add that in to our problem. So using an alpha value of 0.05, and now if we can put it on a new worksheet. This time we'll put it on a new worksheet, click OK, and that will bring us the information out. So again, notice here, it will give us slightly different things than we calculated by hand, but you can see that t-statistic has been identified there as 2.994475 as we did by hand. But the additional things that we get from Excel here are the p-values for 1-tile and 2-tile. Remember, Excel does not know the hypothesis test you're doing. You have to decide which critical value and which p-value you need. So Excel will give us the 2 and 1-tile p-values. It will also give us the 2 and 1-tiled critical values without us having to use the TINV function. So now we can go back and do this test from our template. So our hypothesis test here, we're going to be using a hypothesized mean difference of 0. So in this example, we use mu d equals 0, where mu d means the hypothesized mean difference. And mu d is bigger than 0 for the alternate hypothesis, where D is defined as being blood pressure before minus blood pressure after. So if our mean difference is bigger than naught, it means that the blood pressure before is larger than the BP after on average. So blood pressure before is bigger than blood pressure after is what the outcome would be if we're showing that the mean difference is bigger than naught. Now again, we said to use alpha equals 0.05 in this example, and our degrees of freedom was 10 minus 1, which was 9. Degrees of freedom, 9 degrees of freedom. So if we're writing down now the critical value for T, this is a one-tailed test with 0 in the middle and an alpha value of 0.05 all at one end for the one-tailed test. So 0.05 all at one end with 9 degrees of freedom. So if we'd used Excel here to get TINV, we would be using the one-tailed critical value, which we can see from our Excel file was 1.833. So we'll go back in and write 1.833 for the critical T value, 1.833. So now our test statistic, which we've got in two ways, we've got from the Excel output, we also have from our calculations 2.99 to 2 decimal places, 2.99. So we've done that two ways. We found it in Excel. We also found it step by step by going through the calculations. So the decision in this example, remember that our rejection region says reject the null hypothesis if our calculated test statistic is bigger than 1.833. So that test statistic is clearly in the rejection region. So the decision here is reject the null hypothesis because 2.99 is bigger than 1.833. And this means that we have sufficient evidence to suggest that the average blood pressure is higher when you're waiting to see the dentist than it is afterwards. It is evidence for the researchers to conclude that blood pressure is affected in a way that the mean, while we're waiting for the dentist, is bigger than an hour afterwards. Sufficient evidence to suggest that the average blood pressure before, while we're waiting for the dentist, is higher than afterwards. And that's the end of example 3.